Welcome to the geometry of generalization. In machine learning, we don't just want our models to memorize the training data. We want them to understand the underlying patterns so that they can make accurate predictions on the data they've never seen before. This is the fundamental challenge of generalization. Let's visualize this with a simple example. Here we have a scatter plot showing the relationship between two variables. Notice how the data points follow a general trend, but they are not perfect. There's noise, randomness, just like in real-world data. Now, imagine we build a model that tries to fit every single training point perfectly. This is what we call overfitting. Look at this curve. It's incredibly complex, twisting and turning to hit every single data point exactly. Mathematically, this might be a polynomial of degree 20 or higher. It has zero training error. Perfect accuracy on the data is seen. But here's the problem. This model has essentially memorized the noise in our training data. It's like a student who memorizes answers to specific practice problems without understanding the underlying concepts. Now watch as we relax this curve into something simpler, a smooth sine wave. This model doesn't hit every point perfectly. It has some training error, but it captures the true underlying pattern in the data. This is generalization. The model has learned the signal, not the noise. It's like a student who understands the principles and can apply them to new problems, even if they don't get perfect scores on practice tests. And here's the proof. Let me reveal some data that our model has never seen before. That is our test set. These are new observations shown here in green with reduced opacity. Notice what happens. The overfit model, that complex wiggly curve, completely misses these new points. It performs terribly on unseen data because it was too focused on the specifics of the training set. But our smooth generalized model, it fills these new points reasonably well. It's not perfect, but it is consistent. This is what we want. This brings us to a fundamental equation in machine learning, the generalization error. The true error of our model equals the training error plus a penalty term omega that represents the complexity of our model. This complexity term is crucial. A single model might have higher training error but lower complexity penalty. A complex model might have zero training error but a massive complexity penalty that destroys its performance on new data. The art of machine learning is finding the sweet spot, a model complex enough to capture the pattern, but simple enough to generalize. This is why we split our data, which brings us to our next question. How do we split it correctly? Before we talk about how to split data, we need to understand why a particular way of splitting works. And that comes down to a fundamental assumption in statistics, the i.i.d. observation we could make. The i.i.d. assumption. i.i.d. stands for independent and identically distributed. What you're seeing here is a population of 200 data points. Think of this as the entire universe of possible observations we could make. Let's visualize the distribution of this population. Watch as these points arrange themselves into a histogram, a probability distribution. This curve represents P of X, the population distribution. It tells us how likely we are to observe any particular value. In this case, it's roughly Gaussian or bell-shaped. Most observations cluster around the center with few extreme values. This is our grand truth, right? This is the real world distribution we're trying to learn from. Now, here's a critical question. When we split our data into training and test sets, does the split method matter? Watch what happens if we split naively. Let's say we just take the left half for training and the right half for testing. Do you see the problem? The training set and test set now have different distributions. The training data is skewed to the left, the test data to the right. This is called covariance shift or distribution mismatch. If we train a model on the left side data, we're teaching it about a different world than the one we're testing it on. Right? It's like training for a marathon in the mountains and then running the actual race on a pitch. The test result won't reflect the model's true capabilities. So what's the solution? Randomness. Watch as we shuffle these points. By randomizing the order of our data before splitting, we break any systematic patterns in how the data was collected or organized. Now, when the split 80% for training, 20% for testing. Now, when we split 80% for training, 20% for testing, something beautiful happens. Both sets maintain the same underlying distribution. The training set's histogram looks like the population distribution. The test set's histogram looks like the population distribution. So mathematically we can say P train of X approximately equals P test of X. This is the i.i.d assumption in action. Each data point is independent, which means knowing one point doesn't tell us about another. Identically distributed, which means all points come from the same underlying distribution. When this assumption holds, our test set becomes a valid proxy of the real world, just a proxy. You can't get it perfectly, right? But then our test set becomes a valid proxy for the real world, much better. The performance we measure on the test set is a reliable estimate of how the model will perform in production. This is why random splitting is the gold standard, but sometimes random isn't enough. What if our data has special structures? That's where stratification comes in. Let's talk about a common real-world problem, class imbalance. Look at these data sets. We have 100 data points, but they are not evenly distributed. 90% of them or 90 of them are blue. Let's say these represent normal transactions in a fraud detection system. All 10 are red, the fraudulent transactions. This 9-10 split is actually generous. In real fraud detection, you might see 99.9% normal and 0.1% fraud. In medical diagnosis, rare diseases might appear in less than 1% of cases. Now, here's the danger of pure random splitting with imbalanced data like this. Let's create a test set by randomly selecting 20% of our data. That's 20 points. Oh, look at our test set. It's all blue. By pure chance, we didn't capture a single red point, a single fraudulent transaction. We just went random and then we only picked the normal transactions. This is a disaster. Now, can we evaluate our fraud detection model if our test set has no fraud? Imagine that. We could build a model that just predicts normal for everything and it would score 100% on this test set, even though it's completely useless. This isn't just a theoretical problem. This happens in practice, especially with small data sets or very rare classes, like in this case. The solution is stratified splitting. The word stratify means to arrange in layers. We are going to split our data in a way that preserves the class proportions. First, we separate our data by class. Blue point here, red point here. Now, we can see exactly what we are working with. 90 blue, 10 red. Now, instead of randomly sampling from the mixed pool, we sample proportionally from each class. We want 20% for our test set. So 20% of 90 blue points gives us what? 18 blue points. And 20% of 10 red points gives us 2 red points. Watch as we select exactly these proportions. Perfect. Our test set now has 18 blue and 2 red, maintaining the 90-10 ratio. This is stratified splitting. The mathematical guarantee is shown here. The fraction of class A in the training set equals the fraction of class A in the test set. This ensures that 1. Our test set is representative of the real world class distribution. Number 2, we have enough examples of rare classes to evaluate performance. Number 3, our model sees the true difficulty of the problem during evaluation. In practice, you will use stratified splitting whenever you have, say, classification problems with imbalance classes, multiple categories with different frequencies, any situation where certain subgroups are rare but important. In scikit-learn, it's as simple as adding stratify equal to y to your train test split call. But understanding why this is done matters. That's what separates good practitioners from great ones. Now, we've talked about splitting into training and test. But in real machine learning pipelines, we actually need these. We actually need 3 sets. Let's see why. Here's a critical concept that many beginners get wrong. The test set is sacred. Look at this vault. Inside is our test set. The data we will use to measure our model's final performance, and it's locked, sealed, untouchable. The rule is simple. You don't look at the test set until the very end, not during development, not during hyperparameter tuning, not during debugging. The test set is your final exam, and you don't get to see the questions until exam day. Makes sense, right? So if we can't use the test set during evaluation, during development rather, what do we use? This is where the validation set comes in. Here's our training set in blue and our validation set in orange. And here's the machine learning development loop. First, we train a model on the training data. Second, we evaluate it on the validation data. Third, based on that validation performance, we adjust our hyperparameters, the learning rate, model architecture, regularization strength. We train again with the new hyperparameters. Next, we evaluate on validation again, and then we'll make further adjustments. This cycle repeats dozens, hundreds, sometimes thousands of times as we search for the best model configuration. Now, here's the subtle problem. What if we used the test set in this loop instead of separate validation set? Watch what happens. The vault opens. We pick at the test set to tune our hyperparameters. Every time we adjust our model based on test set performance, we are leaking information. We are implicitly fitting our model to the test set. Not directly. We are not training on it, but we are using it to guide our decisions. After hundreds of iterations, our model has been indirectly optimized for this specific test set. Is contaminated, shown here in purple. When we finally report our test accuracy, it's no longer a reliable estimate of real-world performance. It's inflated, opportunistic, or rather optimistic, and it is a lie. This is called data leakage, and is one of the most common mistakes in machine learning. It's why you see models that perform great in research papers but fail in production. The test set wasn't truly held out. The correct approach is the three-way split. The three-way split. 1. Training set, typically 60 to 70%, used to fit model parameters. 2. Validation set, typically 15 to 20%, used to tune hyperparameters and make development decisions. And then finally the test set, typically 15 to 20%, locked away until the very end. You're done, right? You've already used the validation set to get the results that is impressive before you use the test set only once to report final performance, which is kind of like the mirror of the real world. And then it serves its purpose. The validation set is your development playground. Use it freely, experiment, iterate. The test set is your reality check. Your reality check. Use it once at the end to get an honest assessment of how your model will perform in the real world. And if you need even more robust evaluation, that's where cross-validation comes in. But that's a topic for another video. Now let's see how this concept translates into actual code. We've covered the theory of data splitting. Now let's see how this actually works in code. I'm going to show you two approaches, the scikit-learn way and the PyTorch way. They look different on the surface, but they are implementing the same fundamental concepts we've discussed. Understanding both will make you a more versatile practitioner. On the left, we have the Sklearn approach. This is the most common pattern in traditional machine learning. Here's our data matrix X. Each row is an observation, each column is a feature, and here's our label vector Y. In Sklearn, train test split actually copies and slices the data. Watch what happens. The top portion becomes X train and Y train. The bottom portion becomes X test and Y test. These are separate arrays in memory. The key insight is this. The row indices are shuffled first, but then the data is physically split. Row 0 in X train corresponds to row 0 in Y train. The connection is maintained through position. This approach is simple and intuitive. Of course, it's memory intensive. You are duplicating data, and but then it's perfect for data sets that fit in RAM. The standard for Sklearn, pandas, NumPy based workflows. That's what it is. The code is literally one liner: X train, X test, Y train, Y test is equal to test train test split X Y test size. You set the test size, then the random state for to reproduce it, and then you add stratify equals to Y for stratified sampling. That's it. For PyTorch, the approach is philosophically different. This is the deep learning way. On the right, we have a dataset object. This is an abstraction. It could be images on disk, text in a database, or arrays in memory. The key is that we don't load everything at once. Instead of splitting the data, we split the indices. Watch. Here the indices 0, 1, 2, 3, 4 representing our 5 data points. We shuffle these indices, then split them into two groups. Indices 0, 1, 2 go to training, indices 2, 4 go to testing. Now instead of copying data, we create pointers. These arrows represent the subset or sampler object in PyTorch. They don't hold data, they hold instructions for which data to fetch, which is kind of cool, right? Notice how each index points to a specific slot in our dataset. Even though the indices are shuffled and split, they still map back to their original data points. So when you iterate through a PyTorch data loader, it looks at the next index in the training set. It follows the pointer to the specific data slot. It fetches that specific data point on demand. Now, this approach is first memory efficient, no data duplication like in the case with Sklearn. It is lazy, data loaded only when needed, perfect for huge data sets that don't fit in RAM. This is what you use typically in the factory for the big models. The standard, and it is the standard for PyTorch, TensorFlow, and deep learning workflows. The code looks like you instantiate your data sets, and then you set your training size. Of course, you cast it to the data type, the test sets, and then you also decide the size of your test subset. And then your training data sets, you simply use the random split, and then you pass that to the data loader. Notice shuffle equal to true in the data loader. That's doing the randomization we talked about in earlier. So which approach should you use? If you're working with tabular data, CSV, Excel, databases, or you're working with data sets that are under a few gigabytes, or you're doing traditional machine learning like random forest, support vector machines, or linear models, you should use Sklearn's approach, or you can use Sklearn approach if you wish to. If you're working with images, you're working with video data, you're working with audio data, you're working with data sets too large for RAM, you're doing deep learning neural networks, you should use PyTorch approach. But here's the beautiful part: the concepts are identical. Both approaches, first, the shuffle before splitting, which takes care of the i.i.d assumption. They can do stratified splitting, which takes care of class balance. They can separate train and validation and test subsets, which takes care of data leakage to avoid that. And then they also maintain the connection between features and labels, which is very critical. The implementation differs, but the principles we've covered, generalization, i.i.d, stratification, and avoiding leakage, these are universal. Master these concepts and you can implement them in any framework, any language, any domain. That's the geometry of generalization. Let's recap what we've learned. First, generalization is the goal. We want models that understand patterns, not memorize noise. The balance between training error and model complexity determines real-world performance. Random splitting preserves distribution. The i.i.d assumption requires that our training and test sets come from the same distribution. Random shuffling before splitting ensures this. Then 3, stratification handles imbalance. When classes are imbalanced, stratified splitting ensures every subset is representative. This is critical for rare but important classes. Number 4, the test set is sacred. Use 3 splits: train, validation, and test. Never touch the test set during development, or you leak information and get inflated performance estimates, which is very, very critical. Number 5, implementation varies, concepts don't. Whether you're using Sklearn's array slicing or PyTorch index sampling, you're implementing the same fundamental principles. These aren't just academic concepts, these are the foundations of reliable, production-ready machine learning systems. Get your data splitting wrong and nothing else matters. Your model will fail in the real world. Get it right and you are on your way to build models that actually generalize. Thanks for watching. Now go split some data correctly.